In this video, we discuss how to add two vectors. Let's first look at what this means geometrically. Let's say that we have two vectors x and y. Recall that vectors have a direction and a length, but you can move them around. Take vector y and move it so that its tail is where the head of x is. We call this laying the vector's head to tail. The vector that results from adding the vectors is the net result of following first vector x and then following vector y. The way to compute the vector that results in this way is to sum the components. So here we have vectors x and y. Vector x has components 4 and minus 3. Vector y has components 1 and 5. In order to now compute the vector x plus y, all that you do is add the components together, 4 plus 1 minus 3 plus 5, to yield the vector 5, 2. Now how does this work? If you focus on the first component of x and y, notice that this here is the first component of x, it's 4. This here is the first component of y, it's 1. And notice that the vector x plus y goes across 5 units. Similarly, if you look at the second components of x and y, minus 3 and 5, the minus 3 comes from the fact that x first goes down 3 units, and then the 5 comes from the fact that y goes up 5 units, so the net difference is 2, and that is the second component of the result when you add x to y. Instead of doing x plus y, what we could do is add y to x. Let's see what happens if we do that. So now we start at the same point. We follow y first. Then we lay x and y head to toe. Notice that the net effect again is the same vector, which was x plus y, but is now y plus x. That leaves you with this picture right here. Now, we can do this more generally for general x and y. We start with a vector x, we lay it head to toe with a vector y, or we can start with vector y and lay it head to toe with vector x. In one case we end up with y plus x. In the other case we end up with x plus y. Those are the same vector geometrically. And this is the picture that you should keep in mind. Now if we look at this more generally, where we have two vectors x and y of size n, then if you do x plus y, you look at the separate components of x and y. And all you need to do is add the corresponding components together to come up with the vector x plus y. So the general interpretation is that you start with a vector x, you lay it head to toe with vector y. You notice that the vectors x and y lie in the same plane as does x plus y. That gives you this. And then you could instead have done first y, lay that head to toe with vector x, and then you would have gotten the vector y plus x instead. Now what if we want an algorithm that computes z becomes x plus y? We can take z and view it as its components, do the same for x and y, and then any particular component of z, say zeta 1, just becomes chi1 plus psi 1. We can write this as an algorithm where each component zeta sub I is computed as zeta sub I becomes chi sub I plus psi sub I, the ith component of x plus the ith component of y, right there. And then all you need to do is write a for loop that executes that for I from 0 to n minus 1. To summarize, this is the picture to keep in mind when you add x to y. And if you just look at x and y as the separate components, all you need to do is add corresponding components together to get your vector x plus y.